Very good morning to all. I, Jayashree Radar, Assistant Professor, Department of Mathematics, feels immense pleasure to briefly introduce today's resource person, Dr. Murugendrapa, completed MSc with first rank gold medal, MPhil and PhD in Gulbarga University, served as lecturer, assistant professor in Department of Physics, GMIT Davangere, serving as HOD in Department of Physics, BMSCE, Bangalore. His research interest includes conducting polymer composites. 8 students completed MPhil, 2 PhD, 4 pursuing. and attended many conferences and workshops, presented 45 papers, published 44 papers in national and international journals, major project funded by TechWhip of 5 crore, and many invited talks, followed by life member of Indian Society for Technical Education, Indian Association of Physics Teachers, and Indian Science Congress Association, and awarded merit scholarship for MSc and PhD, and members PhD Scrutiny Committee BTU, and BOE and BOS of various autonomous colleges. With this introduction, I welcome Dr. Murugendra Prakash sir to this session. Thank you.
Thank you, madam. Thank you for the nice introduction. I shall I start now? Yeah. I thanks Shashidhar Gowda as well as Viresh for organizing this 2 days FDP. Yeah. Good morning, everyone. Welcome all the participants. So I'm going to give a presentation on. Can you see the cursor on the screen?
Yes, sir. Yes, it's audible. Yeah.
So my presentation is synthesis and characterization of conducting polymers for sensor application. And this presentation will be mostly useful for the young researchers. So those who are in the field, it is not new thing. Those who are entering to the field may be a new thing. So I'll just touch upon a little bit basics, and then I'll do what actually we are doing in BMS College of Engineering with my students, and what facility we have in BMS College of Engineering also I'm just going to share. Okay, this is what the plan of my presentation. And we greatly thankful to TechUp2, where it is supported with 5 crores grant, because of which only we able to set up all these facilities here. And it is called B.S. Narayan Center of Excellence in Advanced Materials Research. Okay, so I'll take you to the presentation. This is the campus where we stay in Bangalore. It is center of city. It is located in Basanagudi. So a few aerial view of our college. I think most of you might have seen. So those who have not seen, you can have a look. And yeah, so I'll just give you a little bit idea what we are doing. So in the present study, what we did was we have taken a polymer, which is polypyrrole, and we have just made composites with some ceramics like zinc tungstate, strontium arsenate, and then sodium metavanadate. So we made some composites to tailor electrical properties as well to study the sensor applications. So this is a basic idea what I'm going to present today. This is one of my first student research. So that's what I'm presenting. Okay. So the objective of our research is, first we are synthesizing the material using chemical polymerization method, and we are characterizing the composites by a method XCM. I'll go to explain a little bit. XRD, FTIR, Fourier transfer infrared spectroscopy, TGA, and UV visible near area spectroscopies. These are the characterization techniques we are applying. And transport properties we are studying by the method, by the technique with AC conductivity as well as DC conductivity and dielectric properties. And at the end, as an application of these composites, we are using these composites for sensor applications like humidity as well gas. So this is our plan of research we are doing in BMS College of Engineering. Yeah. So I think some of you might not know the field. So those who are young researchers may be useful for this slide what I'm explaining. But for others, it may be common. So please bear with me. So what is a polymer? Since I'm talking polymer, we should know a little bit about polymer. So it is just a chemical where it has repeating molecules with the same chemical structure. So it is just a chemical where it consists of repeating molecules with same chemical structure. This is called polymer. And what is conductance? I think most of you heard about conductivity. Something goes wrong. Hello, sir. Hello.
Hello, sir.
Yeah, can you hear me now? Hello, can you hear me?
Yes, sir, it's audible. Audible.
Yeah, something going on in the background. I don't know what is the problem. Yeah, just I'll share my presentation. One minute. Yeah, now can you see this slide? Yeah. Okay. So this is what the basic I was talking. Coming to conductance. So conductance is nothing but it is an ability of the material to carry electrical charges. This is a basic everybody knows. But what actually we are emphasizing is what is conducting polymer. So conducting polymer comprises both. So it joins, both polymer, which is a repeating molecule, where it gives you conductivity, which can be normally seen only in metals. Okay, so that is what here is coming. Laser pointer. Yeah, now it is fine. So we can see only in metals. So those properties, metals means not in terms of strength or other things. I'm talking in terms of conductivity. So we can find conductivity in case of polymers. Basically polymers are insulators, but still we can find conductivity in case of polymers. So because of which it is called conducting polymer. Okay. So coming to a little bit more about conducting polymers, it was started in the year 1963 by a scientist Natta, where he synthesized a catalyst called Ziegler-Natta catalyst fame for the work which he has done. He awarded a Nobel Prize in the year 1960. This was the basic or the history of conducting polymers. If you go further, in the 1970s, the research brought in this area, especially in conducting polymers. So the first polymer, acetylene, which was polymerized, and it gives you, it's something like a black powder, which was semiconducting in nature. So that was the history of conducting polymer. And two scientists, Alan Eager and Alan McDermott, at University of Pennsylvania, USA. So they found what they found was they found enhancement of conductivity of trans polyacetylene, which is treated with halogen. So once we treat trans polyacetylene with halogen, we can increase the conductivity of that material. And they found the conductivity is increased up to 38 Siemens per centimeter. I'll just give you a little bit idea about what is the range of conductivity for different materials so that you can understand. So because of this, the discovery led into increase in this field research. So the three scientists, Mac Derriman, Alan Eager, and EDK Shirakawa, they won Nobel Prize for Chemistry in the year 2000. So this was the history of conducting polymer. It was started just 20 years back. It is not too old. So these are the three scientists they awarded Nobel Prize for Chemistry for discovery of conducting polymers. Okay. So coming to doping. So doping is something different. I think you might have heard doping in semiconductors. Semiconductor, in case of the doping is ppm. It is parts per million. Here it is totally different. So by the method of doping means adding some extra material to the host. Okay, so that it gives you some increase in the properties. So here we are also doing doping in case of polymers to increase the conductivity, and it gives you more metallic property. Okay, so by the method of doping, it means by adding extra material, we can increase the conductivity up to 10 power 5 Siemens per centimeters. So that is the technique called doping. Now, if you look at this graph, The x-axis gives you the value of conductivity, and we have different materials. Say if you take quartz has very very low conductivity, nothing but insulator. Even if you take diamond, it is also an insulator. Till glass, they are all insulator. So this color gives you insulator. Then if you take this region, it is semiconductor like silicon and germanium with the order 10 power minus 2 Simon per centimeter, sorry, Simon per meter it is. Then comes to metals like copper, iron, silver, they are very good conductors. Its conductivity is of the order 10 power 8. Now, if you look at this above RMR, so conjugated polymers means polymers which are in doped state is called conjugated polymers. So they are initially at insulators. We can make even semiconducting, or we can make till metallics. So by the method called doping. So this is the idea. So we can, polymers basically they are insulators. By the method doping, we can increase the conductivity till you can go up to semiconductors, or you can increase up to metals. Okay, so that is the tool for increasing the conductivity of a polymers. Now, just one more graph to understand what is the relativity or relativistic conductivity for different materials. If you take polyaniline, which is also a very good conducting polymer, its conductivity is less compared to polypyrrole, which is doped with I2. And similarly, polyphenylene, which is doped with ASFI, its conductivity still increases. Like that, liquid mercury somewhere comes here. And then if you look at copper metal conductivity is very, very large. It's almost near to 10 power 6 Simon per centimeter. So what this graph tells you is, by the method of doping, we can increase the conductivity of different polymers. Okay. So it means it can reach till the level of copper. That's what is the graph tells you. Now, some examples to different conducting polymers. We have polyaniline, very good conducting polymer. Polypyrrole, we are interested in this chemical or the polymer. Then polythiophene, polyphenylene, and then polyphenylene vinyl. So these are the few examples of conducting polymer. There are many also. Okay. So the reason why we are taken or we are interested in polypyrrole is because if you look at the conductivity, its conductivity is little good. And if you look at stability, that in doped state, that is also better. If you look at processing possibilities, that is also good. So because of these reasons, when compared to other polymers, if you look at polyacetylene, its conductivity is very, very good compared to polypyrrole, but its stability is poor and its processing possibility is limited. So by comparing this table, when compared to others, polypyrrole is better. And polyaniline is also good, but its conductivity is a little bit less. So most of the work has been done already in polyaniline. That's why we are interested in polypyrrole. It is not, it's not a restriction where only you can take polypyrrole. Any polymer you can work. Okay. Now, a little bit more about conducting polymer, which is polypyrrole, where we are interested. So it was reported by Italian chemist. Actually, it is an interesting conducting polymer. Intrinsic means it is in between, and its conductivity is up to 1000 Simon per centimeter. That is ideal case, but in reality or in practicality, we can increase the conductivity of this polymer or the polypyrrole, which is from 1 to 100 Simon per centimeter. So why everybody is taking polypyrrole for research is because it is easy to synthesize. I'll explain a little bit about how to synthesize, a very simple step, and it is chemically stable. So because of these two reasons, it is more popular in research community. Now, a chemical structure, little bit more about polypyrrole. It is a monomer and it is a polymer. So joining of this pi member with N and S single bond, if you join, it will give you polypyrrole. This is the chemical structure of polypyrrole. Then coming to application, there are vast number of applications. If you just Google it, application of polypyrrole, you can get all these applications like plastic batteries, LEDs for photocopiers, and then micromotor transducers, optical storage, lithography, conducting composites, supercapacitors, solid state sensors, and etc. etc. There are so many applications. If you just Google it, you'll come to know how many applications of polymers you will find. What actually we are doing in our lab? We are taking conducting polymer, which is a polypyrrole, as I told you. Then we are adding dopants. So dopants may be a ceramics, it may be transition metal oxides, or it may be nanomaterials. So my students are working now with nanomaterials. What I'm going to present today is with my first student, which is done with ceramics. And we, by making these fillers or the dopants, we are making composites. So we're interested in these composites. Okay, so what is the property? How it changes when you make composites. So that's what we are working. Okay, this is the idea for research. Now, okay, these are the students which are registered. I'm mainly talking about my first student work today, and these are the PhD titles of the research students. Okay, as I told you, what actually we are doing, we are synthesizing polypyrrole and its composites, and then characterization by different methods, and then transport studies using AC and DC connectivity, and at the end, as an application, we are using in the field of sensors. Fine. So this is what we are doing. Yeah, I think a video which can you can you see the audio video as well?
Yes, sir, we are seeing the video, but it is not audible what the
Oh,
talk he is delivering.
okay, sir. Just a minute then. There is no control here. There is no control here. That is the problem. I don't know, sir. Where is the audio? How to? So just a minute. Yeah, just a minute. I'll make sure it is. Yeah. Now it is audible, sir. Hello.
Yes, sir, audible, sir, audible now.
Thank you.
The Center for Excellence in Advanced Material Research at BMS College of Engineering has been established in the year 2013 under World Bank project Technical Education Quality Improvement Program, TECIP Phase 2, under subcomponent 1.2.1 with a financial grant of 500 lakhs. Under Center of Excellence in Advanced Material Research, high-end research facilities has been established in the form of 4 research laboratories, that is SEM XRD lab, phase change memory materials lab, abrasive water jet cutting facility, and polymer composites lab. The objectives and importance of establishing Center of Excellence at BMS College of Engineering is to develop core competence in synthesis, processing, and characterization of metal matrix, polymer, nanocomposites, and memory materials. At Center of Excellence in Advanced Material Research, we have state-of-the-art research facilities in the form of scanning electron microscope and X-ray diffraction analyzer. The application of scanning electron microscope will be materials characterization of metals, ceramics, polymers, composites, coatings, biological samples, etc. The X-ray diffraction analyzer is primarily used for phase identification of crystalline material and can provide information on unit cell dimensions. Applications of XRD includes phase ID quantification, structure refinement, crystallographic work, polycrystalline thin film analysis, nanoparticle phase ID, nanoparticle size distribution, residual stress, micro diffraction, etc. Abrasive water jet cutting facility is established to investigate machining capabilities of abrasive water jets on advanced materials. Abrasive water jet cutting equipment has a direct drive pump of 30 HP, which can produce 350 megapascals. Abrasive water jets are used to cut different materials ranging from hard to brittle, soft to ductile, thin to thick materials such as aluminum, concrete, polymer matrix composites, metal matrix composites, ceramics, and so on. In this lab, we are working on several areas such as finding machining capabilities on different engineering materials like steels, metal matrix composites, and also we are trying to develop mathematical models for the several outputs like surface finish and depth of cut. And we are exploring the possibility of using abrasive water jet like turning and 3D cutting to produce helical gears. Several batches of UG students, PG students, and PhD scholars are doing the research work in this lab. We also extend this facility to outside students. We have set up polymer composites research lab under Center of Excellence in Advanced Materials Research. In this lab, we mainly concentrate the synthesis of conducting polymer, especially polypyrrole, and fillers like nanometals for making composites. For these synthesized composites, we characterize using SEM, XRD, and FKR. Further, we are studying the properties like transport properties using AC as well as DC conductivity measurements. To measure DC conductivity, we have a Kitley instrument with a constant current source and a nano voltmeter with different temperatures. To study AC conductivity, we have an impedance analyzer with a wide range of frequency from 100 Hz to 5 megahertz. With this facility, we can study AC conductivity. Also, we can study the dielectric behavior of the synthesized composites. As an application of these synthesized composites, we are exploring the possibility of these composites as humidity sensors. With these facilities, we have 4 part-time research scholars and 1 full-time research scholar working under Vishwesvaraya Technological University, Belgaum, under my supervision.
The title of my project in Center of Excellence in Advanced Materials Research at BMS College of Engineering is Synthesis and Characterization of Phase Change Memory Materials. The phase change memories are considered to be a possible replacement for conventional non-volatile RAMs. The facilities which are available in this lab are horizontal rotary furnace, which is used for bulk glassy sample preparation, hot air oven, which is used for annealing purpose, high accuracy balance meter, which is used for weighing purpose, flash and resistive evaporation unit, which is used for coating purpose, dual sputtering unit used for thin film deposition purpose, Keithley source and measure unit along with a custom built probe station, which is used for electrification. Currently, 2 PhD students are working in this lab. We are interested in collaboration for project work or research work in this area or related areas.
I think, yeah, this is what I wanted to share is some student may be interested to do some other work. So I'm just sharing what are the facilities we have in BMS College of Engineering. This is the inauguration. Okay, so I'll go to the main topic. So just this slide tells you how we are synthesizing polypyrrole by a method called chemical polymerization method. So what actually we are doing, this is a monomer taken and an oxidizing agent, and then polymerization reaction takes place, and then we'll get a black polymerized powder. Actually, it is a precipitate, and then we have to filter and then wash it, and then keep it in a muffle furnace for 100 degrees centigrade for 2 to 3 hours, and we'll get a fine powder. Okay, so that is how we synthesize polypyrrole by a simple step. Okay, and then to synthesize, these are the facilities we have. We have polymerization setup, we have ice flaker because we need to maintain at 0 to 5 degree and to dry, and then to keep the sample more except apart from water, we have muffle furnace and other things. And this is the how we are doing a simple setup. Then how we are doing composites, again same procedure. So it is called in situ polymerization. So whatever the dopant we are adding, so here I am showing V2O5 vanadium pentoxide. So whatever the dopant we want to add, you just add it in polypyrrole itself, and then later go with oxidization. So once you do oxidation, you will get a composites. So we are making weight percentage of different composites like 10 weight percent, 20 weight percent, 30 weight percent, 40 weight percent, and then 50 weight percent. Okay, the rest procedure is same. So we are making composites with polypyrrole to increase or to see the variation in the properties of pure polypyrrole. Okay, so we can change any dopants. So I have chosen here vanadium pentoxide. You can do anything. Even it may be a nanomaterial, it may be a carbon pillars, whatever. So that's how we are preparing composites. And I'll take you to few characterization. So this is the instrument we have in our lab. It is called Perkin-Elmer FTIR. FTIR means Fourier transfer infrared spectroscopy with KBR press. So this press is required in order to understand actually this press is required in order to make samples for the FTIR instrument. So once we make the sample, it will give you the result. So if anybody wants to know how it works, I'll have a video. Otherwise, I'll go to the next step. Anyway, these videos are available in the YouTube. So whenever you free, you can just have a look. So actually, how IR works, it has a IR camera, and then it falls on the sample, and then it takes you the characteristic absorption speed. So this is what the sample we are. Maybe useful for the new researchers because you should know the instrument also how it works. So rather than just getting the readings or the graph. Okay, so from that, actually, we are getting a graph something like this, just a sample graph I'm showing. It will give you characteristic absorption peaks, or it may be transmission also. So by analyzing these peaks, we'll come to know what are the bands present in the sample. It is like a signature of each sample. Sorry. Okay, so by taking the picture of the pure polypyrrole as well as the composites, we'll come to know whether really composites has made or not. Okay, that is one characterization. There is one more. Sorry. It's called thermogravimetric analysis. So this is the graph which gives you from a pure polypyrrole. So we are getting two peaks. So one is at this temperature and other is at the other temperature. So this will give you evaporation of water molecule, and this is called decomposition temperature. Again, it depends on the sample. So you have to analyze. So up to this temperature, your sample is perfect. After this, it will be decomposed. You cannot use the sample further. Okay. So this is what the graph of thermogravimetric analysis. And coming to FTIR, this is a standard vibration peaks. So we can assign these single band or double band. So by taking your sample and then analyzing the position of the peaks, you can assign. This is an example of pure polypyrrole. I'm just showing you. So where we observed these peaks, which is due to C double band C stretching, and again, this is the frequency which is due to C double band N stretching. So like that, you can assign each bending or stretching deformation for your samples. So using Fourier transfer infrared spectroscopy. Yeah. Others, can you move, please? Some sound is coming. I request the participants
Hello.
to mute
Hello.
their mic.
Hello.
Yeah.
Participants, please mute yourself.
Sorry. So this is what we have in our BMS College of Engineering. It is called scanning electron microscope. It's a 1 crore instrument. It is available for outside user also by pay and use method. Sorry. And how it works? Again, you can just Google it. You can see a beautiful video how actually a scanning electron microscope works. Because new researchers should know how the instrument works also, rather than getting simply the images and then understanding. So the same Tuscan microscope what we have in our BMS college. So that is the video. Just Google it, Tuscan. It will give you the complete view and how it works and how to get the image, everything. To zoom, what is the magnification, and everything can be understood. Same instrument we have in our college. And we can keep 7 samples at a time. That is the beauty of this SCM. So magnifying images. Okay, I'll take you to next slide. So, okay, this is the same images of our samples. So what I'm going to share is we have SM attached with EDAX, energy dispersive X-ray spectrophotometer. I request the participant to mute the mic. Okay, fine. So we have SCM images for pure polypyrrole, and I have taken one example. It is NaVO3, sodium metavanadate, and if this is a composites. I think you can see some of the NaVO3 particles present in the composites. I'll show you one more image. This is the SCM image of pure fly ash. Fly ash is a product which is it's an waste product which is comes out of your thermal coal, and it gives you a beautiful image. And if you make composites with polypyrrole, you can see the fly ash particles. So by looking this image, you can you can simply say that we have a proper composition made. Okay, so we have uniform distribution of fly ash and we have polypyrrole particles. So okay, so this image will gives you so many information. Uniform distribution is one, how the particle looks and what is the size of the particle, whether it is in nanometer or it is in micrometer, everything you can understand by taking SCM images. Okay. Then coming to next characterization, XRD, it is called X-ray diffractometer. This is the picture of our XRD in BMS College of Engineering. Again, I have a small video how it works and what is the application of XRD. Again, it's a pananalytical we have in our BMS College of Engineering. Same instrument. So those
X-ray powder diffraction has become the global standard for the analysis of crystalline phases in polycrystalline solids and powders. Powder diffraction methods are nowadays used in many fields, from geological exploration through mining and mineralogical analysis, processing of building materials and pharmaceuticals, and onto the research and development of entirely new materials. Here you see the Expert 3 powder, which is our latest multi-purpose X-ray diffraction system based on the fully renewed Expert platform. And just like its predecessor, the Expert 3 powder offers an affordable solution for high throughput, high quality phase identification and quantification. With the latest insights, we have made many significant improvements on the Expert 3 powder. Expert customers have been using their systems for many, many years and very often 24/7. These customers have been praising the Expert's reliability, robustness, and low running costs. Now, with CRISP technology, the Expert 3 powder is taken to the next level of performance, longevity, as well as eco-friendliness. Analytical pioneered the concept of prefix optics, which enables fast experimental reconfiguration without the need for realignment. And just like our high-end Aperion platform, the Expert 3 powder now also employs the second generation prefix, allowing even more accurate positioning of optics when changing configurations. Prefix also makes the Expert 3 powder a future-proof investment, as it can easily be upgraded when new components and applications become available. The Expert 3 powder excels in user-friendliness with a consistent way of working regardless of the application. A complete data acquisition and analysis software suite help new users to intuitively learn the method and generate good quality results right from the start. Whilst powder diffraction based on Bragg-Montano geometry accounts for most of the applications, the Expert 3 powder is very much a multi-purpose instrument and can be reconfigured for specific applications. Using a micro-diffraction setup, one can obtain a diffraction pattern from a very small area. Here is an example of the diffraction pattern of a paint flake. The Bragg-Montano geometry is a reflection method, and for some applications, however, such as the analysis of organic materials or pharmaceuticals, superior low-angle performance is required. Transmission geometry is the solution for this. These data were recorded on the crystalline protein, showing the excellent low-angle performance. When you want to develop phase diagrams, optimize process parameters, or study your materials in operation, in situ X-ray diffraction measurements are an invaluable tool. Expert 3 powder diffractometer supports a number of sample stages with automated control of sample environment, such as variable temperature, humidity, strain, and pressure. The example shown here reveals the crystallographic changes of ammonia borane during the sorption of hydrogen at high pressures. The Expert 3 powder can do more than powder diffraction alone. The size and shape distribution of nanoparticles can be analyzed using small-angle X-ray scattering techniques. And with pair distribution function analysis, you can analyze structural information from disordered materials. Internal stresses of solid objects can be analyzed, as well as the quality and phases of thin film structures. The Expert 3 powder is the proven multipurpose X-ray diffractometer for
you can see those videos in the YouTube. And this is the one example where I have taken again NaVO3 XRD pattern. This is the D values, D spacing. And we have a expert software which will, if you upload these values to this software, it will give you the peak positions and then along with the type of crystal structure, whether it is a monoclinic, orthorhombic, and even the HKL values. Okay, so this will tell you all the information regarding your sample. So these are the HKL values, 110, 101, the Miller indices, whatever you call, and then the type of crystallographic structure, whether it is again cubic or monoclinic or triclinic, rhomboid or whatever. So you'll understand by doing positioning. Okay, so we have expert software to analyze crystal structure. If it is amorphous, it is not useful. If it is a pure crystalline metal, it is really useful. And coming to next, we are studying DC conductivity. So this is a simple setup again, a furnace. The photo quality is not good. And we have a Kittley source meter and a nanovolt meter. We are passing current and we are measuring voltage. So when doing current and voltage, we can calculate conductivity. Again, this one more setup we have. It's a lower version. So how actually we are doing electrical properties? If you know the sample thickness D, and then the area of the sample. If it is circular, you can use pi r square to get the area, and if it is square, use L into V. You will get length into breadth. You will get the area, and then V is the potential across the material, and I is the current. So we are applying current and we are measuring voltage. If you know current and voltage, you can calculate conductivity. So we are using that instrument. We are measuring the conductivity of different materials at different temperatures, at different composites. Again, I'm showing one example. This is a composite polypyrrole with sodium metavanadate. So if you look at the graphs for different compositions, so as temperature increases, the conductivity also almost constant, and as temperature increases further, its conductivity increases. Besides that, if you look at this particular composite, which is 48%, it gives you more conductivity. So depending on your application, if you want better conductivity at this temperature, you can choose these materials. Okay, so when compared to all other composites, 40 gives you better conductivity. If you plot a graph of weight percentage with conductivity at different temperatures, look at the black line gives you 50 degrees centigrade, and then red is at 100 degrees centigrade, and then green is at 150 degrees centigrade. Again, at this blue is 200 degrees centigrade. Now look at all the lines. As temperature increases, conductivity increases, but it is more for 48%. So this percent we assigned as percolation threshold. So below or before or below this percentage, the conductivity less, and even after that, the conductivity less. So for our composites, we proved that 40 is the best because its conductivity is good and other properties also good. So by understanding or by if you want the conductivity at this temperature, this value, then you can use these materials. And the next, as I told you, we have Vancare 6500B impedance analyzer to study AC conductivity. And this instrument has with the sample holder, we can keep the sample here, and we have a furnace. We can increase the temperature of the material, and we can study the parameters. So that is what is the instrument. It is around 14 lakh instrument. And what are the parameters it gives you? So it gives you so many data points. So with respect to frequency, so our impedance analyzer start with 20 hertz and it will go up to 5 megahertz. And we can change the frequency in any way we want. We'll get up to 800 data points for a single parameter. So what are the parameters we are getting? We are getting admittance, we are getting capacitance, and we are getting conductance, and we are getting impedance, inductance, then phase angle, and then reactance, resistance, acceptance, then quality factor, D factor, so many parameters. 13 parameter it gives you with respect to frequency. Then what we have to do with this? So we can plot a graph between frequency versus AC conductivity by using resistance value. We can plot a graph between frequency versus epsilon, which is dielectric constant. You can plot a graph between impedance. You know what is impedance, and later you can calculate electric modulus with simple equations. And even real and imaginary you can plot. Even for dielectric constant you can plot real and imaginary, and even for impedance you can plot real and imaginary, and even for electric modulus you can plot real and imaginary. So many information it will give you with respect to frequency, that is AC. So if you plot a graph between AC conductivity and frequency, again how it varies with respect to frequency for our samples. So as frequency increases, conductivity is a little bit constant till 10^5. Then as frequency increases further, the conductivity increases. So at higher frequencies, it gives you more conductivity. That's what we observed for all the composites. Okay. And again, dielectric constant. As I told you, it may be real or it may be imaginary. Look at this pink line. Pink line is for the pure polypyrrole, and as you make the dopants or the composites, its dielectric value decreases. It means conductivity is more. It's exactly opposite. Then you can plot tan delta. Just I'm showing one or two graphs in order to understand, because this is our research work. If you're interested in any work parallel or similar to this, you can just do it. That's an idea. So as different composites, we have different values for the conductivity or the tan delta. So many things we can plot. I'm showing you here is just AC conductivity with respect to frequency, dielectric constant with respect to frequency, and then tan delta with respect to frequency. Even you can plot with respect to composites also, that I have not shown here. Okay. Then the next, again, this is one of the application we are doing in our research lab. It's called thermoelectric power study. So what is thermoelectric power? So since we are wasting some of the heat energy, why can't we convert that heat energy into electric energy? That is the motto behind this work. And you might have studied Seebeck effect, which is a generation of electrical power, and then Peltier effect, which is exactly opposite, which is nothing but your refrigeration. Fine. So with this concept, we are studying thermoelectric power of our sample, a simple instrument we have in our lab. So how it works? This is the higher temperature. We have a furnace here. We can see what is the temperature of that furnace. It is connected to thermocouple, and we can read the temperature. And the lower one is at room temperature. Usually there is a temperature difference. So this is a sample where we have to keep. The upper surface of the sample is at higher temperature, and the lower surface of the sample is at lower temperature. It means you can keep a water glass here by keeping cold water. It may be 0 temperature, so that the lower surface is at room temperature and the higher surface is at higher temperature. You can see the values also. The lower one gives you 36 and the upper one gives you 66, and you can go up to 200 degree, whatever. And by variation in the temperature, lower one is at low temperature, lower surface, and the upper surface is at higher temperature. Because of the temperature difference, it produces an EMF that is called thermo EMF. So if you connect nanovoltmeter, it gives you better values, and depends on the material. So most of the people are working with thermoelectric materials, because nowadays the heat is simply wasting. Why can't we convert that heat energy into electrical energy? The people are working. This is one of the very good area where if you're interested, you can work. And what actually we're doing, we know delta T. It is the difference between the two temperature. One is the upper surface and the lower surface. and we can measure the thermo EMF. If you measure thermo EMF with the help of nanovoltmeter, and if you know the temperature difference, you can calculate S. So S is called thermoelectric power. So S is called thermoelectric power. How to calculate S? We know the temperature difference delta T, upper surface and lower surface, and we can measure the thermo EMF of the sample. So by using these two values, we can calculate thermoelectric power, and you can plot a graph. So also we can calculate thermoelectric power factor. It is S square into sigma DC. You know S, make it square and then multiply with DC conductivity. You get thermoelectric power factor. So this is the graph we plotted for tantalum oxide. So we again different composites. So this composite gives you better thermo EMF. It means voltage is more for this composite compared to other composites at different temperatures. Again, we can plot a graph with respect to odd junction temperature with thermoelectric power S, what I talked to you. Again, this 50% composite gives you better electric power compared to other composites. I'm talking, this is for polypyrrole and then tantalum oxide. My second student did this work and he published paper on this. And again, we can plot thermoelectric power factor. Again, we have equation to calculate this with respect to 1 by T. And here also we show that 50% gives you more thermoelectric power. Okay, so this is one of the art area where if somebody interested, you can work on thermoelectric power materials, where by changing the temperature between the lower surface and upper surface, we can get the electricity. Okay, then coming to the last part of my presentation, as I told you, we are working on humidity sensor. This is just a block diagram. It is just a glass, which is completely vacuum. We have a vacuum pump because in order to create lower humidity, you need a vacuum pump. And this is a sample holder where you can keep the sample here. And we have a Keithley instrument to measure the resistance, or you can directly connect your AC meter to calculate or to measure the capacitance also. We have hygrometer to measure the humidity of the inside temperature, and we have a thermostat at the vaporizer to increase the humidity of the inside glass. A simple setup, and this is how it looks. It's an actual photograph of simple humidity setup that we have set up in the lab. And what we observed. So if you just plot a graph in distance and relative humidity, as humidity increases, its resistance decreases. So for anything to be a good sensor, it should be a linear variation. It may be increasing or it may be decreasing. It should be a linear variation. Okay, so one more thing we can plot. See, what we observed was, again, 40% gives you better values, and it is almost linear also. We have not plotted the linear regression, and we have not studied further. Anyway, we can calculate sensitivity of percentage of humidity. How? So S can be calculated with this equation, RH2 minus RH1 divided by RH1 into 100. So what is RH1? RH1 and RH2 are the sample sensitivity for humidity at level 1 and level 2. What is level 1 and level 2? Level 1 may be room temperature, or it may be at 20 RH. Level 2 may be a different RH. So you can calculate sensitivity. It's called percentage sensitivity, and you can plot a graph. So percentage sensitivity with respect to relative humidity. So we will get a plot something like this. So what we observe is, see, if you compare this pure polypyrrole, it is not something like linear, like plotted. Its slope is very less. So if you look at other compositions, it's almost linear. So we published this paper also in Sensor Journal. So what we observed was, so as composition makes, we made compositions that gives you better sensitivity compared to pure polypyrrole. So it is a linear variation, and for any composites or any material to work as a sensor, this is very important: response and recovery time. So we are working on this. So what is response and what is recovery time? How fast your material responds to the variation in the sensitivity. So what we did was, we keep in a particular humidity and then change it to some other humidity. How fast it changes to that particular environment. So that can be calculated with this graph, which is almost 100 milliseconds, sorry, 100 seconds. So we are trying to increase this. If the response and recovery time is less than 10 seconds, then it will be a very good sensor. Okay. So if it is more than, then depending on the situation, suppose if you are looking for LPG sensor, it should give you information immediately, not after 1 hour. See, if it gives you information after 1 hour, then everything will be gone. So what actually we are trying is, we have to make the response and recovery time much less as possible, so that it's an instantaneous information. So that's what we are working. And recently we bought, before COVID, a sensor instrument for different gases. That is what we made. It is a laboratory made humidity sensor. That's what I have shown, and we have worked on it. But we have procured a sophisticated gas sensor unit. We have a mass flow controller. It's a mass flow controller. This is a gas inlet. Whatever the gas if you want, you can make to pass through, and the gas will come to this chamber. This is again vacuum chamber where you can keep the sample here. So first create vacuum and then close all the valves. So after creating a vacuum, keep the sample and then allow the gas whichever you want to do for sensor. Then depending on your sample absorption, it gives you sensitivity that can be measured with this instrument, and the same results can be get in PC. So by using this, we'll come to know whether your sample is really a good sensor or not. Okay, so this is not started working. It means before COVID only we procured this. Now we are working on this with different gases. So it's a gas inflow and then a mass flow controller, and it goes to this chamber and then it comes out. And depending on the environment, it gives you some information. So that can be captured with this PC. Okay, so this is what we are doing in BMS College of Engineering. So I think I have done with my presentation. So thank you all the participants, and you can just Google it. You can go to BMS College website. You will get all my profiles and details. And even for paper published, you can go to Scoopus and you can get the details. And so just a few more points I wanted to share with you. If somebody interested to work in some other field, we have air quality monitoring system in our research in our college. So where we have a 1 crore instrument, it captures all the data. If anybody interested to do research, you can come and join. And we have air direction or the wind direction. These are the two labs what I shown you, polymer composites research lab with all the facilities available. And these are the facilities available in our BMS College of Engineering. And this is one PM particulate sampler where one of our colleagues is working. And again, we have online radon thoron monitor and then gamma survey meter. So one of my colleagues is working on radon. So we have instruments to do this. And again, one of my colleagues is working in nanometers. We have a collaboration with nanometers. So now we are doing nanometal with polymer composites. And how it works, this is the hydrothermal pumps to synthesize nanometals with different facilities we have. So if anybody interested to join PhD, you can come and approach us. We have the details here with you. Yeah. So I done with my presentation. If anybody has any queries, it's open for you. Thank you. Hello.
Hello, dear participants. If you have any queries, Professor Murugendrappa is open for you to clarify your queries. Please ask. You unmute your mic and then you please ask your queries.
Hello, sir.
Tell me.
Myself, Madhu KN. My question is, how can we decide the scanning voltage of SEM to obtain for a smaller area like 10 to 5 micrometer for metals as well as alloys and polymer composites?
Voltage will not play an important role in image processing. Okay, it depends on how deep you are going. It depends on the instrument. Fine. Okay. Voltage will never play any role on your image capturing. It depends on the type of instrument. Suppose we have instrument, it will go up to 50 nanometer. Some instrument will go up to 1 micrometer. Whatever may be the voltage you apply, the maximum image you will get is up to 1 micrometer. Okay, so it depends on the sensitivity of the instrument, not the voltage you applied. Is it clear?
Okay, sir.
Any other questions? Participants, did you understand something? If you are really interested to do collaboration, you can we'll do some work if you are interested in this field. And I have shown you other fields also where my colleagues are working. If you are interested in any field, you can approach us. Any other doubts? Tell me. Hmm? Hmm. Okay, actually it is just a image clarity. So SEM will give you, it is electron scanning, whereas it is field emission. Okay, it is just a technique difference that will give you better quality of images compared to SEM. FASM is far better compared to your SEM, like your XID and AFM. No, it does not depend. So if you want better quality images, you will have to go for FASM. If you want the medium quality images, SEM is sufficient. Yeah. Any
Hello?
other questions? Yeah, tell me.
Hello, participants. If any other participants are interested in asking your queries, you please raise your questions at the earliest. Thank you, Murugendrappa sir.
If there are no questions, sir, 1 minute. I should thank the principal of Tontadarya College of Engineering, Dr. M.M. Avati, and I should thank Dr. V.T. Maglat. Viresh is my friend for making this FDP. I also thank the convener of this program and other coordinators of Tontadarya College of Engineering. Thank you, one and all.
I must acknowledge that, Professor Murugendrappa, as soon as we approached him, immediately he has accepted. Due to some technical problem, we were unable to, make the arrangement of one more, resource person. And immediately we approached Murugendrappa sir, and without any fraction of second delay, he has accepted, and he has delivered a wonderful session, and he has ignited such an interest in me also today, that he has actually made the tour of all of us. Felt like that, we made the tour into BMSC College of Engineering research laboratories, and he has explained very lucidly all the procedures as well as theoretical backgrounds, insights. He has given very excellently. As himself, I know very personally that a very excellent teacher also, and he is a rare blend of teacher and researcher. What I feel personally, from the beginning of his student, from his student life itself, I know him. He was a very meticulous worker. He is a gold medal awardee, and it itself tells, his involvement in any of the work to the greater extent. Today's his explanation is the reflection of his involvement, what I feel personally. Sir, we, Tontadarya College of Engineering faculty, management and principal, and all the research scholars in this college express deepest gratitude to you, and we are very much eager, and whenever it requires, we will approach you to make some progress in the research in our field whenever. And we, on behalf of our research scholars, I request you to cooperate whenever it
by all
comes to
means.
such an
By all
extent.
means. By all means.
Thank you, sir. Sir.
Yeah, thank you very much. Thank you all the participants. Yeah, good luck to all.
And I request Professor Kavya Abhigiri Madam to present a vote of thanks to the gather.
Hello, am I audible, sir?
Yeah, very much.
Okay. So myself, Assistant Professor Kavya Abhigiri, Department of Physics, Tontadarya College of Engineering, Gadag. It's my privilege to propose the vote of thanks on this occasion on behalf of Principal, HOD, Dean R&D, and staff members of Basic Science. A very hearty vote of thanks to Dr. Murugendrappa MB sir and Jaisuk sir, yesterday's guest, for your gracing your important work and sharing with us your findings and opinions today. Sir, thank you very much, sir.
Thank you. Thank you.
We had a very good session today, and I would like to thank our HOD, Professor Sneed Patil sir, Dr. V.T. Magaraj sir, Dean R&D, for the support and guidance they have extended to us. Lastly, I thank convener Sheshtar Koda sir and all the faculties of Basic Science, their involvement in completing the task, and all the participants for their active participation. Thank you, one and all. Thank you, sir.
Yeah, sir. Thank you, sir. Thank you very much.
Thank you, sir. Okay. We will be leaving now, sir.
Yeah, sir. Shall we leave now?
Yes, sir. Yes, sir. Bye, sir.
Yeah. Thank you. Thank you, sir. Thank you. Bye.
Thank you.